slide, Lindsay?
Yeah, if you want to advance the slide, you can. I just want to take a moment to introduce Sarah. Some of you know her and know the brilliance that she brings with her, and others, she may be a new face. So this is Sarah Lonberg-Lew, and she works at the Adult Numeracy Center at TERC, which is in Massachusetts. So she's in a whole different time zone here. And she's worked in the field of adult numeracy for 7 years, both as a classroom teacher and has provided a lot of professional development for math and numeracy teachers. She's a consultant for SABES, the System for Adult Basic Education Support, Mathematics and Adult Numeracy Curriculum, and Instruction PD Center at TERC in Massachusetts. And she develops and facilitates trainings and workshops and assists programs with curriculum development. And she is also very connected to the Adult Numeracy Network, ANN, and she is the treasurer for them as well. So comes with a wealth of experience, and we are very privileged to have her here today. So I'll turn it over to Sarah.
Thank you, Lindsay. That was, boy, I think you did that better than I could. So, yeah, by the way, if there is no bandwidth issue, I'm happy to see your faces. It's always nice. So feel free to turn the cameras on if you like. And all right, so I guess time for the big reveal. The kitty's name is Scout. She does sometimes go by her nickname, which is Jean Louise. So yes, Scout is her name. So yeah, welcome to oh wow, another cat named Scout. Look at that. Welcome to Proportional Reasoning, Strategies That Make Sense. So let's jump right in. I'm going to give you just a quick overview, and I have just 2 objectives for today, but they're big ones. One of them is to identify and kind of put a name on 2 intuitive strategies that we use for reasoning proportionally already, strategies that we use when we see friendly numbers, and then to look at how we can apply those strategies to proportions that have unfriendly numbers. So our agenda is that we're going to do an activity at Desmos. If you're not familiar with Desmos, please don't worry. It's very friendly, and there are lots of people here who will help you out if you have problems. We'll look at a place where proportional reasoning comes up in geometry class. And through those 2 things, we're going to get our 2 strategies. Then we'll be extending our reasoning to less friendly numbers. And my hope is to provide some time for practice in breakout rooms. But that is really just a hope at this point. I don't want to rush things just to give you time to practice something that we haven't had time to really cover. So if we don't get to that, I will leave you with some practice tasks and trust you to talk to each other and continue your learning that way. So, so what we'll do is we will go to Desmos. So we're going to start with this activity, and you can go right to student.desmos.com and put in the code that you see on the screen. Whoops. And I'm also going to, I just hit Control V instead of Control C, so I managed to paste something completely random into my notes. There's the link directly to the activity. So it should be pretty clear when you get to Desmos, it will give you an option to sign in. You can sign in if you want. You can also continue without signing in. If you sign in, then if you come back to this link later, you'll be able to revisit your own work. If you don't sign in, it'll be like you're starting new. It's not really a big deal either way. So, so do what you're more comfortable with. And at the end, I will share with you the link to the activity to the teacher side, so you can use this with your students. So I see, let's see, I see a lot of you showing up in the activity. That's great. You're already on screen 1. So you can see now that that Scout is actually relevant to the work that we'll be doing. And your task here in this activity is to put this beautiful picture in a frame. And on screen 2, you will have the ability to move 2 sliders to adjust the length and the width of the width and the height of the photograph in whatever way feels right to you. And then you can drag it into the frame. You don't have to worry if any parts of the photograph stick out of the frame, because those will be trimmed off, so it will look beautiful. And just, take your time with this. Really, adjust it until it looks good to you. And when you're ready, you can go on to screen 3 and describe your reasoning, but really take your time and play with it. And also you should know that your names in this activity have been changed to the names of famous mathematicians. I emphasize famous because if I didn't change them, they would still be the names of mathematicians, just not famous ones. So, when you share your answers, your colleagues will not know where they came from. I'll give you a minute to play around with that. You folks are doing great. I'm looking at, there's a great variety of approaches here. Just going to give another minute. So if you, I'm hoping you can see what some other people have put as the way they reasoned about it. It's a wonderful thing about Desmos. I can see what everybody wrote. You can see what some people wrote, but as the teacher, it's great to be able to see how you're all thinking. Okay, so what I'm going to do now is I'm going to show you just a few snapshots from a few people's enlargements. So let me switch my screen share. Can you all see the pictures? Yeah, okay, good. So my question to you then is to look at some of these, or look at these pictures here, and especially if you see one that looks different from how you were reasoning about it, how do you think people were reasoning? You can identify them: top left, top right, bottom left, bottom right. What are your thoughts?
I had not thought about the concept of zooming in beyond the cat just to fill it up. So whoever zoomed in to like get the whole head, I think that one looks awesome.
Yeah, there's definitely some free choice and artistic expression here. Yeah, the bottom left got the best of her face. Yeah.
It might just be my subjective memory, whatever you want to call it, but the top right, the dimensions, and then the close-up of the face, the looks more accurate to what I remember the original looked like, whereas the top left and bottom right, she's thinner. So
yeah, Rebecca says the same thing, that some of them seem kind of skinny, and bottom left looks like the person might have wanted to get the head to fit perfectly in the frame with each ear pointing into the top corner. Yeah, could be, but it is the case. So we have 4 different outcomes here, and some of them look kind of not quite like the original picture, right? There's 2 things going on. There is the cropping and there is a distortion. And in some pictures we get a distortion and in some we don't. So what is it? And by the way, I'm not putting any judgment on this. I mean, this was the artistic vision of everybody who participated. So, you know, you may choose that you like the distorted picture, but what is it that we can do that makes the picture come out undistorted? What strategies were applied here?
I just did multiples of the length and the width to try and get it to fit, and it didn't quite make it. So then I went to smaller multiples of it. Instead of going by multiples of 1, I went multiples of 0.1 until it looked like it fit right.
So multiplying the length and the width by the same number, but adjusting what number you're choosing. Yeah.
Yes.
Yeah. Anything else?
I think that's made me stressed out because I really wanted to, like, I looked at the 3 and the 4 in our information, but anytime I tried to use whole numbers, it didn't work right. And so then I got into decimals and I was like, no, because if she's going to ask us to calculate later, I don't want a decimal. That sounds hard. So I thought about that. Ooh, Rebecca says it's hard to get a rectangle into a square.
Yeah. So I guess that's one of the things that makes this activity challenging, is that the proportions, the dimensions, or the ratio of the dimensions in the original picture are not the same as what we see in the frame. So it was meant to sort of give you a little bit of that struggle. I hope it didn't stress you out too much, but it's not really possible to sort of do this perfectly, which means I'm taking perfectly to mean undistorted, and you haven't lost any of the picture and you haven't got any white space in the frame. Like, that's just not going to work. And there's some reasoning we can do about that. That's something that that we could think about more. But I'm going to go back to the slideshow now, and I will say there are a few more screens in the activity which I blocked you out of because I'm just drunk with power. And but I am going to share the link to the teacher side, and you'll be able to access those later. So let's see, I'm going to go back to the slideshow. And we'll just talk a little bit about, what we're thinking when we're trying to create an undistorted enlargement of the picture. And one intuitive way to create an undistorted enlargement is to just take our two dimensions and multiply them by the same number. Like we might double the dimensions. Doubling is the sort of simplest multiplicative relationship we have. So there's some intuition behind this. And the intuition is if we make the picture twice as wide, then we should make the picture twice as tall. And that's how we're going to avoid distortions. And if you play around with the sliders, you'll see that if you do that, if you treat both dimensions in the same way, the picture is not going to get distorted. I actually noticed when I was playing with it, and I thought this was pretty cool, that if I was just eyeballing it, which some people did, I noticed that when I moved one slider, like when I moved the width slider and then I moved the height slider to kind of compensate, I didn't move the height slider as far as I had moved the width slider. So I could see that it wasn't a matter of like adding the same thing to both dimensions. It was more a matter of treating them the same way multiplicatively. So, if we look at this more formally, it looks like this. This is probably an equation that you've seen a lot. We use these two arrows to indicate that we're multiplying both numbers in the proportion by the same thing. So in other words, we're getting an undistorted enlargement, and we're getting something that has the same relationship to the picture we started with by treating both quantities in the picture the same way. We're doing the same thing to both of them, or we're multiplying them by the same number. So I'm going to call this intuitive strategy reasoning across. Right? We're reasoning across from one ratio to the other. And it doesn't just work with enlarging pictures. Reasoning across makes intuitive sense in a lot of contexts. So for example, if I double the amount of flour in a recipe, I should also double the amounts of the other ingredients. That's what you would imagine you do if you're scaling a recipe up. If you're scaling it down, you treat all the ingredients in the same way. At least that's what you do in math class. If you talk to a baker or a chef, you might find that actually things are not as proportional as we like them to be in math class. But for now, let's live in the realm of math. Yes, unless you're adding more chocolate, in which case, just lots and lots of chocolate, I think, is the approach. So if I work 3 times as many hours, I should earn, anybody want to finish the sentence?
3 times as much money.
If I work 3 times as many hours, I should earn 3 times as much money. Whatever I do to the number of hours I work, I should also do to the amount of money I make. If I can walk 2 miles in 40 minutes, it should take me half as long to walk half as far. So I'm treating these two quantities in the same way. That's reasoning across. And I will say that, it's important to say, yes, I'm treating them in the same way multiplicatively. I'm not adding the same thing to both numbers. We know that that's not how it works. But when you look at these contexts, you can actually, it makes a lot of sense that it wouldn't work to add the same thing. For example, if I work 3 more hours, do I earn $3 more? Hopefully not. Right? That doesn't make a lot of sense. Or it could say, if I can walk 2 miles in 40 minutes, does that mean I could walk 3 miles in 41 minutes? I'm adding 1 to each thing. Definitely not. I mean, 2 miles in 40 minutes is already kind of fast for me. So I could not walk an extra mile in an extra minute. So there's our ratios again, just to connect that to that more formal notation with the arrows going across. But to summarize, reasoning across means treating both quantities in the same way to get a new situation that's proportional to the original situation. So I have some ratio in the original situation. If I treat the quantities the same way, I get a new situation that is proportional to the original. I'm loving this chocolate side conversation that's going on here. I'm glad I have chocolate in the house to get into after this is over. Okay, so let's look at then a different place where proportional reasoning comes up. And this is where proportional reasoning comes up in geometry class. So it's a little bit more formal, but it's a pretty common place where we encounter it in the topic of similar figures. And there's a nice connection between what we started with, which was enlarging a picture, and the idea of similar figures, because while you can have sort of complicated, intimidating, and formal definitions of similar figures, you can also just say that two figures are similar if one is an undistorted enlargement of the other, just like we saw distortions and undistorted enlargements with the picture. So I'm gonna say that these two triangles are similar. Anybody want to agree or disagree or back me up on that? You got a thumbs up, that's good. How do we know these two triangles are similar? The same relationship between the height and the base, the same ratio of the height to the base. Yeah, so what we're seeing here, yes, please feel free to speak out loud, is that the height of these triangles is twice the base, or if we multiply the base by 2, we get the height. And that's a different kind of reasoning than we were using with creating an undistorted enlargement, because here we're not reasoning from one triangle to the other. What we're doing is we're seeing a relationship in one triangle and seeing the same relationship in the other triangle. So if you look at this kind of in the more formal, yes, Mark, thank you. You can also multiply the height and base of the smaller triangle by 2 1/3. Yeah, I'm gonna get to that in a minute. So so this is what it looks like, though, with these arrows that we're used to drawing, that we can see that this is a multiplying by 2 relationship, that from the base to the height, we see multiplying by 2, and it's the same relationship between, the same relationship in each triangle. So you see the arrows are not going across from one ratio to the other, but they are within each ratio. And yes, Danielle, you're right. There is a smarty pants in this group, and he has noticed that there's a relationship across as well. So yeah, there's a relationship across, but I don't think very many people would look at the numbers 3 and 7 and go, oh, I know, you multiply by 2 1/3, right? That's not as easy to spot as a doubling relationship. It's not as familiar, it's not as accessible. So we can reason across in this situation, but it's not as intuitive to do it. It makes more sense here to reason within, because that doubling relationship is easier to spot, but there is that number there. I put a question mark because I didn't bother to figure out what it was. So we're gonna have to trust Mark that it's 2 1/3, but if we multiply 3 times 2 1/3, we should get 7. If we multiply 6 times 2 1/3, we should get 14. So yes, it is. Thank you, Andy. So if it wasn't, the reasoning would still have been sound, that when we're looking at equivalent ratios, we can treat both quantities in the same way to get another ratio that's equivalent, or we can create a new ratio that has that same relationship in it, which would be reasoning within the ratio. Okay, but before we talk more about reasoning within, we're going to take a little side trip here. I'm going to give you a bonus ratio. So here are some more triangles, and these triangles are similar to the triangles we looked at on the last screen. They all have that same relationship where the height is twice the width, or twice the base. 8 is twice as big as 4, 4 is twice as big as 2, 5 is twice as big as 2 1/2. And you know, in the pair on the right, there's a nice whole number relationship across as well, which is not too hard to spot. In the pair on the left, There's also a whole number relationship there, but it's not as easy to spot. And it's not that it isn't there, and depending on your fluency and comfort with these numbers, you might immediately see it, or you might have to do some work to figure it out. But it's good to know that that relationship exists. But within all four triangles, within all four triangles, we have that 2-to-1 relationship, which we can make as many triangles as we want that have that same relationship. So there is something, I'm going to say, special about the relationship of the height to the base of a right triangle, which is what we're looking at here. And what I'm going to do is I'm going to take all of these triangles and I'm going to kind of stack them up like this. And because they are all similar, because their angles are all the same and they all have those same proportions, the hypotenuses of the triangles are making a nice straight line. And I'm going to add a few other elements to this picture. And now, yeah, look, oh, you folks are awesome. So I was going to say, what does this look like to you? But I already see Amber saying it looks like slope. So in fact, this is often a picture that we draw when we're talking about slope, right? We're showing that that ratio of rise to run is the same no matter where we go on the line. And yeah, slope is one of those things. When I taught slope, I would teach its rise over run. I thought that was a much friendlier way of teaching it than y2 minus y1 equals x2 minus x1, which is really kind of intimidating, and students can get caught up in trying to memorize it. But and like rise over run is important, but it feels to me like a lot of the time when we approach slope, we approach it starting with the formula. This is how you find the slope, without talking a lot about what slope is. And my opinion is that slope is a beautiful answer to a really important question. And the question is, how steep is that line? How steep is it? And there's more than one way you can answer that, but it's quite elegant to answer it by saying, well, it goes up 2 every time it goes over 1. And I've told you everything you need to know about how steep the line is by explaining this ratio to you, to say it goes up 2 every time it goes over 1. And when you think about the question, yeah, road grade signs too, yeah. When you think about the question, how steep is something, it would feel really natural to answer that question with an angle. And why are we answering it with a ratio instead of an angle? And my feeling is that the reason we're answering it with a ratio is because that ratio usually is very meaningful in context. Usually if we're graphing a line, we have a reason for graphing a line. We're graphing some relationship between real quantities. And so for example, if I am graphing the number of dollars I earn as a function of the number of muffins I sell, now all of these triangles have meaning in that context, except maybe this one. This one says I will earn $4 if I sell 2 muffins. This one says I will earn $8 if I sell 4 muffins. This one's a little bit weird. You know, maybe I'm not going to be able to sell 2.5 muffins. But this one down here, yeah, okay, now it's the muffin top. That's true. We're going to have to do a lot of work to figure out if that's exactly half a muffin, but it's a good idea. So, but this triangle down here on the bottom is giving us the unit rate, $2 per muffin, and that's the slope. So the slope is meaningful in context. Yeah, could be an average, sure. Yeah, so I think that's my feeling about why it's so beautiful and elegant to answer the question about steepness with a ratio, because when we're graphing a line, we usually have a reason for graphing the line. And the slope, whenever you graph a line in context, that slope is going to be meaningful. So that's our little side jaunt into slope. I would stop to ask if you had any questions, but this group seems like you're gonna put them right in the chat if you do. And I am trying to keep up with that. So let's now look at that idea of reasoning within. Just like we did with reasoning across, how does it make sense in different contexts where we might reason proportionally? The weird triangle is an answer to, if we each kick in $5, how many muffins do I get? Yeah, awesome. It's great that you folks can make sense of these abstract things in context. So if we go back to a baking or a cooking example, if a recipe has twice as much brown sugar as white sugar, then when I scale up the recipe, it will have twice as much brown sugar as white sugar, no matter how I scale it up, provided I'm doing this mathematically and I don't know much about baking. It's going to, that relationship is going to be preserved. Similarly, if I'm paid at a rate of $18 per hour, if I work 35 hours, I will be paid at a rate of $18 per hour. Actually, these examples, I think, are showing up a lot of ways as well where we expect things to behave proportionally and they don't, right? If you are getting paid an hourly wage, you may get paid overtime, and that's where the proportionality of it falls apart and you get something different. But in, you know, when we're just trying to get a sense of what it means to reason within a proportion, it means that the ratio, the relationship that I see in the original situation, I also see in the second situation or in the new situation. If a panoramic photo is 3 times as wide as it is as tall, then an undistorted enlargement of it will be 3 times as wide as it is tall. We would see that same relationship. So if we look at our ratios from our similar triangles, it's the relationship within each triangle that we're looking at. We have the ratio in one triangle and we are seeing the same ratio in the other triangle. And those two ratios are, in this case, pretty easy to recognize. So we recognize that 6 is twice as big as 3 and 14 is twice as big as 7. The relationship between 3 and 7 is harder to spot. It's there, but it's harder to spot. So reasoning within means identifying a relationship in one ratio and applying it to another ratio. Any questions, comments, complaints, concerns? I'll give you a chance to try it. So here are some ratios for you to try, or proportions, I should say, for you to try, and see if you can find the missing number. Think about what strategy you're using. Are you reasoning across or are you reasoning within? And when you feel ready, you can put some of your ideas in the chat. So we have already some disagreement, which is great. Because easy, like this, making this decision about reasoning across or within is about what's easier for you, and easy is subjective. Is there a relationship between where the number's missing as to which strategy is more helpful? That's a really good question. That's usually what I say when I'm not prepared to answer a question or I don't intend to answer it. But no, it is. I mean, I'm thinking about that question. Actually, let me put it out to the group if folks have an idea. Is there a relationship between where the number's missing as to which strategy is more helpful? So we have a few people saying it doesn't seem like there is a relationship. It depends on the relationships you see between the known numbers. Does the unit rate impact whether the reasoning within is friendly? Like if the unit rate has friendly numbers? Yeah, like a unit rate is usually something we would see within one ratio. So if that rate seems really clear to you, then reasoning within is probably a good choice. Sometimes either direction is going to work well if the numbers are friendly, and but it really does depend on, you know, what jumps out at you. So let me, would somebody be willing to explain the reasoning that they used for proportion B?
I can. This is Danielle.
Yeah.
So for B, I looked at the 15 and the 20, and that didn't seem super easy. So then I looked at the 3 and the 15, and I'm like, oh, that's easy. It's 15 divided by 5 is 3. So then I'll do 20 divided by 5 and get 4.
Nice, thank you. So you saw that relationship within, and so one thing that's a little bit different from some of the other ones we looked at before is Danielle spotted a division relationship instead of a multiplication relationship. And that is something to do with where that missing number is. Are you thinking multiplicatively? Are you thinking about multiplication, or are you thinking about division? And you might just flexibly go between them. You might still see it as multiplication and say 3 times 5 is 15. What number times 5 is 20? Or you might see it as division. 15 divided by 5 is 3. 20 divided by 5 is our missing number. There's more than one way to do it. You can think flexibly. You can do it in the way that feels most natural to you. Yeah, or Andy says 3 is 1/5 of 15. So you can be thinking about fractions. There's so many ways you can do it when you recognize some kind of relationship in those numbers. But what about when you don't? So, you know, we're here to talk about how can we use our intuitive strategies, our ideas about across and within, when the numbers are messy. But don't worry about that for right now. Just think about, like, when you see this proportion, what would you normally do? What would your students do? What have you been trained to do when you see a proportion like this?
One of the things that I like to do is try to get my brain going into it, like to try to figure out something that's reasonable. So trying to think about something that might be like way too low or way too high, as for what our missing value is. And so I know that 16 is really small in comparison to 110. I can kind of think about it as like 16. I could round down to 10 because that might be easy to compare to 110, or round it up to 20 since it's closer to there. So I'm knowing that X is probably going to have to be a pretty big number, because 84 is a lot bigger than 16. So kind of thinking in my mind that if I want to see if my answer is reasonable, that might be something I need to do.
Yeah, estimating is really powerful. we also have some ideas about maybe simplifying the ratio with the numbers given. And let me pause for a minute because Rebecca, I think I missed a question that you had earlier.
No, I was just thinking about the comment about where the X sits. And I just wanted to remind, well, when with proportions, we can move those fractions around. If we swapped the order of them, then now the X is moved, but the relationship's the same. I can, 16 over 110 equals 84 over X has the same relationship as 110 over 16 equals X over 84. So just seeing that that's kind of a fluid situation as far as where the X sits can really be moved around, but have the same relationship.
Yeah, as long as you're thinking about, how things relate to each other, and using those across and within relationships does sort of prepare you to restate the proportion in different terms. Yeah. Okay, so we had the idea of estimating to find X, which is an awesome idea. We had the idea of maybe simplifying some of these numbers to make it easier to reason about. Any other thoughts about how you would approach a proportion like this?
I approach it trying to think about like how many 16s, like thinking that it was messy, but maybe not too messy. If it ended up being too messy, I don't think it would have worked. But so I was like 16, and I kept kind of thinking about going up by 16s. And so 5 16s is 80. And then 4 was left over. And I was like, oh, I see a relationship between that 4 and the 16, like it's a quarter of it. And so then then 5 and a quarter, so I looked for the across, but thinking about that. But if it had not been something as clean as 5 and a quarter, that wouldn't have worked.
Okay, so you looked for that across relationship, even though it didn't really jump out at you, because you knew it was there. You maybe were willing to push for it. And Lindsay says cross multiply and divide, is that a viable strategy? Yeah, we have also the idea of simplifying and estimating. Yeah, so I think you are like a wonderful, creative and flexible group, and that if I ask this question in a more general population, I think that this idea of cross multiplying and dividing would be a pretty common answer. That is what we are trained to do when the numbers are messy. So I'm going to go into how we can solve this without resorting to cross multiplication, but before I do, I'm going to just get on my soapbox a little bit and talk about why I don't like cross multiplication, just in case anybody, I want to be clear about where I stand on this. So number one problem with cross multiplication, as far as I'm concerned, is that I can't make sense of what's happening the way I can when I reason across or I reason within. So here's an example of a proportion that makes a lot of sense to me. If I can read 5 pages in 8 minutes, I can read 10 pages in 16 minutes. I see that across relationship. If I double the number of pages, I double the number of minutes. That makes a lot of sense. But if I look at the cross product, I multiply 8 minutes by 10 pages and I get 80 page minutes. And it's great because I get 80 page minutes on the other side. That's 16 minutes by 5 pages is 80 page minutes. But my only problem is, like, what is a page minute? I don't know. That unit doesn't have anything to do with the reasoning. Yeah, it could be a name for a cat, page minutes, but it's not something that comes up as I reason about this situation. The number 80 doesn't come up as I reason about this situation, and this really weird unit of page minutes does not come up. So I'm doing something that that doesn't make sense, and my strategy should make sense to me. I mean, it's reasoning, right? I shouldn't do something that doesn't make sense. Rebecca says students always get confused on when to cross multiply fractions and when to multiply fractions straight across. Thank you, Rebecca, because that is my reason number 2. Proportions look like other situations that have their own procedures that are more difficult to remember than cross multiplication. So if you glom onto this cross multiplication as easy, quick strategy to remember, then when you see something else that looks kind of like it, and you can't really remember what to do there, yeah, students will go to that cross product, even though it doesn't work in those situations. Yeah, and then this is my big problem. My main objection to the cross product, to cross multiplication, is it is not reasoning. When we do this, we are not reasoning. And the concept that we are exploring here is called proportional reasoning. It makes sense in context. There are intuitive ways to think about it. Students, adults, anybody can reason flexibly, proportionally. And then we take that beautiful thing that's so intuitive and has so many different ways to reason about it flexibly, and we teach a procedure that you can do without thinking. And yeah, I think problem solving should involve thinking. That is my opinion. It's telling students how without having them understand why. Yeah. And one solution that I've seen to this is to try to teach why cross multiplication works, which we can do, but it's not really, I don't know, I don't find it very satisfying. And I'm going to say these difficult proportions, these messy numbers, we can solve them by reasoning. And we've already actually talked a little bit about how to solve them with reasoning. So one of the things that's going to help us reason about this proportion is to give it some context. So, so here's a real world context for this proportion. I folded paper cranes as decorations for my sister's wedding. Those are actually them that I folded. I folded a lot of paper cranes, 100 paper cranes in all. And the first 16 cranes took me 110 minutes. And I want to know, how long did it take me to fold the remaining 84 cranes? So here is some context to help us think about these relationships. And what we'll do is we'll go through this situation, reasoning across and reasoning within, and see how we can apply these strategies even when the numbers are not so friendly. And a lot of the things we're going to do, I feel like some folks in this group have already come up with, which is great. So when we're going to reason across, the first thing we can do is start with an estimate. That's already come up. And if I think about the reasoning across, I'm going to look at that relationship between 16 cranes and 84 cranes. And 84 is more than 5 times as much as 16. So if I folded more than 5 times as many cranes, then I should expect that it would take me more than 5 times as long. Okay? Just like we looked at those other examples of reasoning across in context, whatever we're doing to one quantity, we're doing to the other quantity. More than 5 times as many cranes takes more than 5 times as many minutes. So using that to make an estimate should take me more than 550 minutes. You already have the sense that this is quite a large project. I didn't do it all in one sitting. So this is great, but suppose I want a more precise answer. I would really like to know exactly how long it took me, which is already a silly question because I don't fold paper cranes like a robot, and they're not all going to take me the same amount of time, but you know, we're in the silly realm of everything working out in the world of math. So I want to know, I'm going to ask the question, how many times as many cranes are really in the second set? We have an estimate. We know that it's about 5 times as many, or a little bit more than 5 times as many. But what I want to know, and it's important that I ask this question, is precisely how many times as many cranes are in the second set. And Mark had some nice reasoning about, because he already asked that question, where he said, well, you know, I know that 80 is 5 times 16, and then there was that 4 left over, and that helped him reason about it. But if you don't have, if that doesn't come to you, or if you don't feel like you can reason like that, you can also think about inverse relationships. Inverse relationships is a great fancy high level term to use. It sounds like we're doing algebra, which we are. You can also call it a fact family, which is, you know, maybe more friendly, but some people think it's something for little kids. I don't. But the idea is that if we're looking for a number that when we multiply it by 16, we get 84, since multiplication and division are related, we can divide 84 by 16 to find that number. It turns out that that number is 5 1/4, 5.25. And, you know, I picked, actually, I said these were going to be unfriendly numbers. They're not as unfriendly as they could be. I did pick numbers that are sort of, I don't know, mildly hostile, I guess, but so 5 1/4 times as many, but if they had been, if it had been 16 into 87 or something even more hostile, this division would still give us the number we're looking for. Then we just might have to make a decision about rounding and how many decimal places we wanted to take. But in this case, we found precisely that there are 5.25 or 5 1/4 times as many cranes in the second set as in the first set. And that means that it should take precisely 5 1/4 times as many minutes. Yeah, I'm not really sure where mildly hostile fits in relationship to unfriendly. I hadn't really thought through that scale, but the point is that across relationship is there, right? When the numbers aren't, I love that the cat thing is continuing through this. When the numbers aren't so friendly, it doesn't mean the relationship isn't there. We just have to work harder to find it. And that might mean going to a calculator, or it might mean reasoning about fractions, but it's still there. And I can figure out by multiplying by 5 1/4 that it took me exactly 577.5 minutes to fold the remaining cranes. Yeah, teaching across and within is going to reinforce what the equal sign means. That's an interesting observation. Yeah, because we are looking for those same relationships. So just to sort of quickly recap, what does it look like to reason across in a situation where the numbers are just a little bit hostile? What we did was we made an estimate. Always a good idea to start with an estimate, especially with proportional reasoning, because if you mess up your proportional reasoning and you've made an estimate at the beginning, you are going to know that you've messed it up, because usually if you do the wrong calculations or something, you're going to get a very unreasonable answer most of the time. Then we asked the question, how many times as many cranes are in the second set as in the first set? And we used division to answer that question. So we're thinking about those arrows that go across. The arrows are usually telling us what to multiply by. They can also tell us what to divide by. In this case, we use division to figure out what to multiply by. And then we use the answer to that division to find our precise answer. So, I'm showing you a slide here with a set of steps on it. And I just want to say, like, don't memorize these steps. Okay, because that's not why we're here. We're not here to memorize steps. This is a kind of reasoning. So focus on understanding the reasoning, and you can practice the reasoning. And it's not about remembering the steps, but they will come fluidly to you if you are focusing on the reasoning. And maybe we'll get some time to practice reasoning, we'll see. But before we do, let's look at the same situation with reasoning within. And when we reason within in context, often what we're doing is we're talking about rates. Not always, but a lot of the time, ratios are rates, and by rates, I mean like how fast something is happening. Relative to something else. I don't necessarily mean a unit rate. I know that that's also a definition of the word rate. But here, I was doing a task in time. And so these ratios, this ratio of 16 cranes in 110 minutes tells me something about how fast I was folding cranes. And because this first ratio, the one where we have both numbers or where we know the whole situation, is a ratio of cranes to minutes, that means that I maybe am thinking about the number of cranes I can make in 1 minute, or maybe I'm thinking about the number of minutes it takes me to make one crane. And it's pretty important actually that I pay attention to what I'm thinking about here, that I know what rate is going to make sense for me to reason about here. And it took me 110 minutes to fold 16 cranes. So the number of minutes it took me was a lot bigger than the number of cranes. So what that means is if I think about how many cranes I can fold in a minute, I don't think I'm going to like that number very much. That's a number that is like, I can't fold a crane in a minute. That's going to be a small number. So I think for me, it makes more sense to think about how many minutes it takes me to fold one crane. So what I'm going to look for is the number that I can multiply my cranes by to get my minutes, because that's how many minutes it takes me to make one crane. And I'm going to start with an estimate here too. And I noticed some people talked about this, or this has sort of come up before. Mark looked across to find a relationship between 16 and 84. And we also heard, I think Amber was saying, well, 110 is a lot bigger than 16. So we're looking at that relationship, and the relationship is very accurately described as a lot bigger. I think that's a really good description of the relationship, because it's not that easy really to, for me at least, to estimate how many times as big 110 is than 16. So I'm just going to make those numbers friendlier just to give me some kind of sense of what's going on. So instead of thinking, what can I multiply by 16 to get 110? I'm going to round the 16 to 20 and the 110 to 120 so that I have a nicer number to think about. It's a rough estimate, but it's really good to start with an estimate. So the number of minutes it takes me to, or the number of minutes is about 6 times as big as the number of cranes. In other words, it takes me about 6 minutes to fold each crane, or I'm folding at a rate of about 6 minutes per crane. And the way I estimated here, I'm not even really sure if that's an overestimate or an underestimate, but you know, it's a rough estimate. So, and I can use it at least to say that at this rate, I could multiply my 84 cranes by 6 minutes per crane and say it would take me about 504 minutes. Since we already know the answer to the question, that might give you a sense of whether that was an overestimate or an underestimate. But if you've forgotten the answer, that is fine too, because it's not really about the answer. So just like before, we need to ask a question. And the question is sort of informed by the estimate that we already made. We estimated that it was 6 minutes per crane. If we want to have a more precise answer, we've got to ask, how many minutes does it really take to make one crane? And when we know that answer, and we've already sort of figured out how it's used in the proportion, we'll be able to use it to find X, or to answer the question of how long will it take me, or how long did it take me to fold the remaining 84 cranes. So just like before, we can use our inverse relationships or our fact family to say that if I multiply 16 by some number, I will get 110. Therefore, if I divide 110 by 16, I will get that number. And that's definitely a harder number to spot, but you know, we all have calculators near at hand these days. You can use your calculator if you like, or you can just trust me. It comes out to 6.875 minutes per crane. So my 6 minutes per crane was a little bit of an underestimate there. It was closer to 7 minutes per crane. Being able to estimate is so important, but our students are often resistant because it's not taught in school enough, so they're not familiar with it. Yeah, and another thing actually I think is that when estimation is taught in school, it's often taught as a goal in and of itself and not as a tool for problem solving. So, you know, I've seen a lot of students when I used to teach in K-12, and it would say, you know, estimate and then solve. And what they would do is they would solve and then they would round off their answer and say, that's my estimate. So, you know, they didn't understand how to use estimating as a strategy, but it is so important. And a lot of the time in the real world, it's good enough. It definitely would have been good enough in this situation, because this idea that I can fold a paper crane in 6.875 minutes exactly is kind of a ridiculous idea. So it's sort of better for me to say, it takes me 6 or 7 minutes to fold a paper crane. Yeah. So if we do the multiplication here, 84 cranes times 6.875 minutes per crane, it does come out, luckily, to the same number of total minutes, which is really good. Let me take a look at this comment here. Finding across and within relationships is so much more intuitive when working with proportions. It's really exciting to be able to bring this back to students. So much math brought in. Yeah, estimating, multiplying, dividing, etc. Would you ignore cross, multiply, and divide if students asked about it? That's a good question. And hopefully you'll have an answer to it by the time we get to the end here, because, and I know sometimes this puts me kind of out there, but yeah, like I wouldn't teach it. I don't think it's a valuable strategy. Yeah, estimating can make people anxious, true. Yeah, and that's something I think that we have to just practice with to get more comfortable, that we need to stick with it. That's how we get more comfortable with stuff. So let me do a quick recap. And so that the question about what would I do if students asked about cross multiplying, if I don't come back to it, remind me, because I'm intending to. So here's the recap of how we reasoned within in this situation. We made an estimate. We asked a question to get a precise answer for that estimate. How many minutes does it take to make one crane? We used division to answer that question. Whether you use multiplication or division to answer the question is going to depend on what the question is. Doesn't even seem worth it to let students practice it. Yeah. And we multiplied the number of cranes by the answer to that question to find our value for X. So I think we are going to have some time for you to practice in breakout rooms, which is awesome. Before we do, I'm just going to call our attention to mathematical practice number 8, which is look for and express regularity in repeated reasoning. And I just want to point out that it says repeated reasoning. It doesn't say repeated application of a rote procedure. That the way that you develop fluency is by practicing the reasoning. And when you go through this reasoning over and over again, it becomes more and more ingrained. It becomes more and more natural and more fluent. Yeah, so the cross product, maybe it can be a tool in their toolkit and it's broken. So they have to use other strategies. Yeah, but Mark, that's what I'm getting at. It's easier to recreate steps you built through reasoning as opposed to just following them. They will come back to you. That's like when you practice reasoning, you're going to learn something. And when you learn something, if you learn something and then forget it, as soon as you start thinking along those same lines, it will come back. Whereas if you memorize something and forget it, you're going to need somebody else to tell it to you again. So what I'm going to do is I'm going to give you a frame to practice the reasoning. And this is a frame that we've already been using. I'm going to say it sort of as steps, but I don't mean it to be steps that you have to follow like a robot, but it's just in case this is helpful to identify, am I thinking across or am I thinking within? And feel free to change your mind on that if whatever you choose doesn't work out for you. But then asking a question, finding the answer to that question, and then using the answer to find the missing number. So for example, with the paper cranes, when we looked at the within relationship, we asked the question, how many minutes does it take to make one crane? We found the answer using division. And then we used that number with multiplication to find the missing number. So like I didn't put the operations in the steps of the frame because which operations you use will depend on which question you ask and which direction you're reasoning in. There's a lot of choices still to make. If you want a super brief summary of this, if you think about the proportion with the arrows, the reasoning across or reasoning within, that what we're doing here is we are finding the numbers that go on the arrows and then we're applying them. That's a super brief way of doing it. So, I have some practice tasks for you, and I'm going to put a link in the chat. You can grab it here. You can also take a picture of that QR code, and that will take you directly to the document. But if you want to have it on your computer, this might be easier. So, what we'll do is we'll go into breakout rooms. Let's see, we have 20 minutes left, I think. I'm just going to talk in relative terms because I don't understand the way that you people keep time out there in the Midwest. So 20 minutes left. So I'm going to say, let's take about 15 minutes in the breakout rooms, and then we'll come back together. And I'm going to encourage you to take a little time, a little think time quietly before you talk to each other, and then start to talk through these tasks together and how you reasoned about them.
All right, before I open the rooms, just to double check that, see if anyone has any questions. You've got the link. I will put you in those rooms for...
And the link is to a copy, so that's so that you can edit it if you want to. And it's your own copy, or you can use scratch paper.
And everyone should have the ability to share their screen. So if there is one person in a breakout room that wants to share, so you're all looking at the same thing, you can feel free to do that as well.
And you can annotate too.
Mm-hmm.
So many options. All right, I'm going to open those rooms. Enjoy. If you get lost on your way to your break room, let me know. We'll see you in a little bit.
Right. Okay, welcome back, everyone. I hope you had a chance to try out some of this reasoning. I imagine that you didn't have a chance to do all 5 of the tasks, so you have more time, or you have more to occupy you later. I really do think, you know, you are looking for regularity in repeated reasoning. So I really strongly encourage you to, even though you already have this strategy or this procedure that works, you know, to push yourself to try this way of reasoning and help it feel more fluid and fluent. And even, you know, if you looked at one of those tasks, like you looked at the oranges and the dollars, and you thought, like, let's go to unit rates, how many dollars per orange? Great. Now, what if you try it the other way? Can you think about reasoning across? That will double the number of practice tasks you have. So there's an extra gift for you. Okay, I am sharing my screen, right? Yes, okay,
yes,
good. So let me just sort of wrap up with the payoff, which is, and I hope this comes back to that question that I sort of ignored earlier, which is that when you reason across or within, you are doing 2 computations. It's the same number of computations you do with cross multiplication. Sometimes they're even the same computations. They're not usually in the same order, but it's exactly the same amount of work. So, but when you reason this way, you know what you're doing and you know why you're doing it. So, like, my answer about cross multiplication is I just don't think there's any reason to do it, because the main thing that it's got going for it is that it's efficient and quick. And this is also efficient and quick. So especially when you solidify that reasoning in your mind. So I would, you know, that's my feeling is I would go for that. And also to say, you know, that this way of thinking, this reasoning across and within with unfriendly numbers, is just a tool in your toolbox for proportional reasoning, and there are lots of other tools. So don't throw away the rest of the toolbox just because you have this now, because there are lots of ways of reasoning intuitively, proportionally, and adult students bring a lot of strategies that they've developed on their own. So this is just something to add to your toolbox. So in my remaining minute, I will say that if you like reasoning in ways that make sense, there's a great community of people who like reasoning in ways that make sense. And if you're not already a member of the Adult Numeracy Network, please do join. We'd love to have you. And I'm here also representing the Adult Numeracy Center at TERC in Cambridge, Massachusetts, which is also worth checking out. And my contact information is here as well. And I don't want to keep you, but I will stick around if you want to chat or have other questions at the end. But I will say thank you so much for your awesome participation. It's been really fun.
Thank you so much.
I have a question for you, Sarah. This is Carl.
Go ahead.
Hi. Have you noticed that if these strategies have really reduced any math anxiety for students?
That's a really good question. I can't say that I have personally experienced that, but my guess is that it would. I mean, it's, you know, a lot of the anxiety in math comes from trying to remember how to do stuff and not understanding what you're doing and not feeling like you have any agency or control. And here, you know, these are strategies that they have flexibility built into them. You have to make decisions, and those are your decisions. And there is not one right way. So, you know, I think a lot of math anxiety comes from teacher says, this is the way to do it. You must do it this way, or you get a big red X on your paper. Even sometimes you don't get credit, even if you got the right answer, but you did it not the teacher's way. So, I would imagine that this would help with anxiety.
I had a calculus professor who said that he used to make fun of us because people wanted partial credit for, you know, getting close to the right answer, you know. And so that's an example of what you just said, you know, not getting the right answer. And then, of course, if you're writing a math proof, you know, it was always an all or nothing thing. So created a lot of anxiety, that's for sure.
Yeah, as teachers, we can be a lot more flexible and recognize when our students are reasoning and appreciate that reasoning. And I think that goes a long way as well. It's not just about, you know, you have to get what X equals and you have to get it precisely and you have to get it the way I told you to get it.
All right, thank you.
Abby says too that when a student can sort of assess for themselves whether an answer is correct, that also alleviates some anxiety. Was I going to share the Desmos activity? Yes, thank you so much. I absolutely was, and I have it right here in my notes, and I wrote it in big bold text so that and made it red so that I wouldn't miss it. And yeah, I missed it. So let's see, here it is. I will give you this. So you do need this link to get to the teacher side of the activity. So if you lose it, I'll make sure that Lindsay and Patsy have it, and Gail as well, so that they can share it with you. And yeah, I'll unlock the other screens for you. Let's see, I have this, I still have the dashboard open. So I will unlock the other screens. Find it. Zoom out of the way. I could go play with the other screens now.
I think I will go ahead and stop the recording here, but people are welcome to stick around for a couple minutes.